Hello everyone. In this lecture, we will discuss about the number systems of digital electronics, and we will start the discussion with the definition of the digital electronics first. So basically, digital electronics is a branch of electronics which deals with digital systems or binary number systems. This is the definition of digital electronics. Now, number systems are basically divided into four types in digital electronics. The first one is decimal number system. So all the numbers from 0 to 9 are decimal numbers. That means 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So all these 10 numbers starting from 0 to 9 are called decimal number system. Next is your binary number system. A binary number system consists of only two numbers, 0 and 1. Third one is octal number system. So basically an octal number system consists of the values or the numbers from 0 to 7. So total of 8 numbers are there, 0, 1, 2, 3, 4, 5, 6, 7. So total of 8 numbers are there in octal number system. Next is hexadecimal number system. So basically hexadecimal number systems are starting from 0 to F. F means 15. So 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. Then the alphabets A, B, C, D, E and F. So these are all hexadecimal number systems. So these are basically the four categories of number system. Now this topic is very important from the semester point of view, as well as this topic is important for the competitive examinations also. So these are some assignment questions which is useful for semester examination. The first question is, what are the differences between analog signal and digital signal? Second one is, what is the advantages of octal number system? Third one is, what is the advantages of binary number system over decimal number system? Next one is, what is the value of 1 byte? And what is the value of 1 nibble? Okay, so these are the basic questions from the digital electronics. So as there are four categories of number system, any number system can be converted to any other number system, such as a decimal number system can be converted to a binary number system. A binary number system can be converted to a decimal number system. Hexadecimal number system can be converted to octal number system. So basically any number system can be converted to any other number system. So here one process is given, conversion of decimal number system to binary number system, where 13 is a decimal number system. Generally a decimal number system is represented with base 10. So the equivalent binary number system will be 1101. Okay, so how will you convert a decimal number system into binary number system? This is the complete process. These are the complete step. The first step is divide the decimal number system by 2 successively. Okay, so this particular method is called double method. So the step number 1 is divide the decimal number system by 2 successively. Note down the remainder after each division. Continue the division process until you are not getting the quotient equal to 0. Okay, so as you can see, the decimal number 13 is divided by 2. Okay, so 2 6 are 12, the remainder is 1. 2 3 are 6, the remainder is 0. 2 1 are 2, the remainder is 1. Now what I have to do is that I need to write down the number from bottom to top. I need to read this number from bottom to top, and the value is 1101. 1101 is my binary number. Okay, so this is a small example. We will discuss the whole process by understanding the few more concepts about the number system, such as LSB, which is called least significant bit, MSB, which is called most significant bit, LSD, which is called least significant digit, MSD, which is called most significant digit. Okay, so format of writing decimal number. As you can see, 235, a decimal number is given which has a base 10. So this number, the 5, is called your LSD, or you can say least significant digit. And this 2 is called your MSD, or you can say most significant digit. So how will you recognize? As you can see, this is a unit place. So 5 is placed in a unit place. So I can say that this particular digit carries the lowest weight. So this particular digit carries the lowest weight. And this particular digit carries the highest weight. As you can see, 5 into 10 to the power 0. So this is the lowest weight. 3 into 10 to the power 1. Next highest weight. Next higher weight. Then 2 into 10 to the power 2. The highest weight. So this is called my most significant digit, and this one is called your least significant digit. So we have mentioned here LSD is the digit which carries the lowest weight, MSD the digit which carries the highest weight. Similarly, LSB in case of binary number system, least significant bit, and MSB is the most significant bit. Okay, so as you can see, a binary number is given here 11010, which has a base 2. So all binary number system must be written like this in this structure. The base is 2. So this first bit carries the lowest weight. That is why it is called LSB. And this one is called MSB because it carries the highest weight. So it can be written as 1101 is this 1 into 2 to the power 0. Why 2 to the power 0? Because it is a binary number system. That is why I'll multiply 1 into 2 to the power 0 plus second bit 0 into 2 to the power 1 plus 1 into 2 to the power 2 plus last 1 into 2 to the power 3, which is equal to 1 plus 4 plus 8, which is 13. And this is my decimal number system. So in this way, a binary number system can be converted to a decimal number system also. Now let us solve one example. The example is 10110101 and it is a binary number system. Let us convert this number system into decimal number system, binary number system into decimal number system. So as we know, this particular one carries the lowest weight. So I can write 1 into 2 to the power 0. Then the second is 0, 0 into 2 to the power 1, which is equal to 0. Third one is 1 into 2 to the power 2, which is 4. Next is 0 into 2 to the power 3, which is 0. Next is 1 into 2 to the power 4, which is 16. Next is 1 into 2 to the power 5, which is 32. Next one is 0 into 2 to the power 6, which is 0. And the last one is 1 into 2 to the power 7, which is equal to 128. Once you add up all these numbers, you will get the decimal number, which is 181 is the result. So the decimal equivalent of this binary number is 181. Now let us convert a binary number which is having a binary point into the equivalent decimal number. So as you can see in this question, the binary number is given as 1011.010. So in this binary number, we have two parts. One is whole number part and second one is fractional part. Okay. So for this whole number, this first value is my LSB and this value is my MSB. In the same way for the fractional part, this is my LSB and this is my MSB. So let us calculate the result for whole number part first. So for the whole number part, this 1 into 2 to the power 0 is equal to 1. Then 1 into 2 to the power 1, which is equal to 2. Then 0 into 2 to the power 2 equal to 0. And finally 1 into 2 to the power 3, which is equal to 8. And once I add up all these value, I get the result 11. Now let us calculate for the fractional part. As this is LSB, this is MSB. So it will carry the lowest weight. So 0 into 2 to the power minus 3, which is 0. Then 1 into 2 to the power minus 2, which is 1 by 4. And 0 into 2 to the power minus 1, which is 0. And the result is 1 by 4, which is 0.25. So my result is 0.25. And overall result is 11.25, which is in decimal, which is the decimal equivalent of this binary. Let us solve one more example of similar kind. So the binary number is 110101 101, and this is a base 2. Determine the equivalent decimal number. So let us calculate for the whole number part. So this is my LSB and this is my MSB for the whole number part. So this can be written as 1 into 2 to the power 0, which is 1, then 0 into 2 to the power 1, which is 0, then 1 into 2 to the power 2, which is 4, then 0 into 2 to the power 3, which is 0, then 1 into 2 to the power 4, which is 16, and at last 1 into 2 to the power 5, which is 32. Once I add up all these values, I get the result, which is 53 for the whole number part. Now put a decimal sign, put a decimal point, and calculate for the fractional part. So for the fractional part, this will be LSB and this will be MSB. So the result will be 1 into 2 to the power minus 3, 0 into 2 to the power minus 2, and 1 into 2 to the power minus 1. So the result is 1 by 2 plus 0 plus 1 by 8, and the result will be 62. So my decimal equivalent will be 53.62. Now let us calculate a decimal number into a binary number. Let us calculate a decimal number into binary equivalent. So the number is 25.35, which is in decimal. I need to convert this decimal into binary. So as we discussed already, for the whole number part, I have to go on divide it by the value 2. So let us divide the whole number part 25 by 2. So the result is 2 1 ja 2, 2 2 ja 4, the remainder is 1. Then 2 6 ja 12, the remainder is 0. Then 2 3 ja 6, the remainder is 0. 2 1 ja 3, remainder is 1. Now write down the binary number from bottom to top. So this will be 11001 and the result is 11001. This is my binary equivalent, where this one is my LSB and this one is my MSB. Now let us calculate the binary equivalent for this fractional part, 0.35. So for that, I need to multiply the fractional part with 2. So 0.35 into 2 is 0.7. Keep the whole number, which is 0, and multiply 0.7 again with 2. The result is 1.4. Take the whole number and multiply 0.4 with 2. The result is 0.8. Again take the whole number, then multiply 0.8 with 2. The result is 1.6. Take the whole number, which is 1, then multiply 0.6 into 2, which is 1.2. Take the whole number, which is 1, and multiply 0.2 with 2. The result is 0.4, and take the whole number. Now this process goes on, or you can say this is a never-ending process. So I got the result 11001.010110 bar, which is my binary number. So in this way we can convert a decimal number into the binary number system. Now let us take one more example. This time we will take only a fractional part, 0.625. So I need to convert this decimal number into binary equivalent. So multiply 0.625 with 2. The result will be 1.25. So I will preserve this one and I will multiply this 0.25 with 2 again. The result is 0.50. Now I will preserve this 0 whole number and multiply this fractional part again with 2. The result is 1.0. So my result is 1. Now this 0 fractional part when multiplied with 2 will produce 0 only. So finally I got the result 0.101. So I need to read this binary from top to bottom. So 0.101 is my binary equivalent for this particular decimal.